Alright, today we're going to have a look at the second part of topic 7, special parts of a triangle. Part B. So previously we have talked about part A, which include bisectors and perpendicular bisectors of a triangle. And today we are going to have a look at the concept of angle bisectors of a triangle, medians, altitudes, and some challenging problems involved special parts of a triangle. Okay, so following our discussion in our previous part, we're going to have a look at the third key points, angle bisectors of a triangle. First of all, can you prove that the angle bisectors of a triangle are concurrent? We can actually prove this by using the following method. We start much as we did with the perpendicular bisectors. We consider the intersection of two of our angle bisectors. So angle bisector K and angle bisector M. So this angle equals this angle equals this angle here. And point I in the diagram, since I is on the bisector of angle CAB, it's equidistant from AC and AB, right? We have already proved this in our previous lesson. Remember that? If it's on the angle bisector, then it's equidistant to each side of the angle. Since it's on the angle bisector of ABC, it's equidistant from line AB and line BC as well. Therefore, I is equidistant from all three sides of the triangle. Specifically, since I is equidistant from AC and BC, I is also on the angle bisector of ACB. Well, actually, we have proved this in our previous lesson as well. We found a special circle. Then, following this method, we can actually find a special circle centered at the intersection of the perpendicular bisector, which is, in this case, is somewhere here, inside the triangle. And next, let's see if the intersection of the angle bisectors is the center of a special circle too. Alright, now let's consider this question here. The angle bisectors of triangle XYZ meet at I, and perpendicular segments from I to the sides of the triangle are drawn as shown. First question, why is IR equals IQ equals IP? Second question, suppose we draw a circle with center I and radius IP. Does the circle hit segment YZ at any point besides P? Next question, show that circle from question B is tangent to sides XZ and XY at Q and R respectively. Okay, I'll give you 3 minutes to consider this question by yourself, and then we'll have a look at the solution together. Okay, let's have a look at the solution together. The first one is very straightforward, right? Because that's the point of intersection of angle bisectors, and we know that any point on the angle bisectors are equidistant to both sides of it. So in previous problem, we found that the intersection of the angle bisectors of triangle XYZ, is equidistant from the sides of XYZ, since IR, IQ, and IP are distances because they are perpendicular to each side, right? So IR, IQ, IP are distances from I to the sides of triangle XYZ, and I is the intersection of angle bisectors. Then we know IR must equal IQ, which equals IP, right? Can you follow me? Okay, second question is a little bit complex, but we can still show that the circle with center I and radius IP doesn't hit YZ. We can show this anywhere else. We can show that circle with center I and radius IP doesn't hit YZ anywhere else is to show that all other points on YZ. For example, you can choose any arbitrary except point P. Let's call this point V. Are actually outside the circle. So as shown here, point V is on the point of YZ, right? Besides point P. From right triangle IPV, the hypotenuse is of course longer than the leg IP, right? Because because of the Pythagorean identity. So IV is larger than IP. Or circle consists of all points exactly IP from I. Since V is further than IP from I, it must be outside of the circle here, outside of this circle, right? Any point besides P must be outside of the circle I. Can you see that? We have just proved that, right? There's nothing special about the point V. As long as it's not point P, it must be outside of the circle I. Therefore, it's impossible for the circle with radius IP to hit the line YZ at a second point, which means that circle I must be tangent to YZ, right? And you can use the same method to prove actually that circle is tangent to line XZ and also tangent to line XY. Therefore, it's actually tangent to all of the three sides of that circle, that triangle, right? Okay, question C. Since IP equals IQ equals IR, the circle with center I and radius IP goes through Q and R. 2. For the same reason as in the previous part, we have just proved that this circle is tangent to all three sides of X, Y, Z. Did you get it? So this is an important property of the intersection of the three angle bisectors of a triangle. So let's have a look at summary here. The angle bisectors of a triangle are concurrent at a point called the incentre. So this point I is called the incentre. This point is equidistant from the sides of the triangle. This common distance from the incentre to the sides of a triangle is called inradius. because of the circle with center I and this radius is tangent to all three sides of a triangle, this circle is unsurprisingly called the incircle because it's inscribed in the triangle, meaning it's tangent to all three sides of the triangle. Incenter is usually denoted by letter I, and the inradius is usually written as R. Okay, you can compare this property with the circumcenter, circumradius, and circumcircle we have just talked about in our previous lesson. Remember that? The circumcenter is the point of intersection of the perpendicular bisector of each side, whereas the incenter is the point of intersection of the angle bisectors. Okay, careful with the difference. Okay, I'll give you 2 minutes to have a look at the property here, and we're going to have a look at another important property after that. Okay, have you written this down? Alright then, let's have a look at another property by using this example. So given that E is on AC such that BE is a bisector of angle ABC, can you prove that AB over AE equals CB over CE? Okay, first of all, you need to draw a diagram to illustrate the concept here. So basically we have a triangle ABC, right? E is on AC such that BE is an angle bisector of angle ABC, which means this angle equals this angle. So can you prove AB over AE equals CB over CE? Okay, I'll give you a hint. When you see ratios, what do you think of? Usually we think of similar triangles, right? So can you find any similar triangles? If not, can you make or create similar triangles? You have already had a pair of equal angles, right? So if you can find another pair of angles, then actually you can find a pair of similar triangles. Of course, from this diagram itself, we cannot find another pair of equal angles, right? So how about we draw a extra line here? So from point C, we can draw a line. Well, let's call this point X such that CX is parallel with CB. How about that? And extend BE to a point. Okay, let's call the intersection point here as X. This is possible, right? This is doable. And then we know because CX is parallel with AB, then this angle here must equal this angle here, right? ABE equals angle CXE. Then can you find any similar triangles now? Okay, and we have just proved that angle ABE equals angle ABX, let's call it X. Okay, angle ABX equals angle BXC. And also angle ABX equals angle XBC, right? This is already given to us. So this side equals this side because this is an isosceles triangle. Okay, and parallel lines gives us this angle equals this angle, right? Then we have triangle ABE must be similar to triangle CXE, right? According to AA similarity, right? Can you follow me? Therefore, corresponding sides must be proportional. Therefore, we know AB over AE must equal CX over CE. Since we have already proved CB equals CX, then we can conclude AB over AE must equal CB over CE, right? Did you get it? Okay, then we have actually proved another important property of the angle bisectors of a triangle. So let's have a look at the summary here. This is called the angle bisector theorem, which states that if E is on side AC, such that BE is the angle bisector of angle B in triangle ABC, then we have the following conclusion. AB over AE equals CB over CE. You get it? Also, you should think of this anytime you have a problem involving length and angle bisectors. Okay, I'll give you 1 minute to write this down, and we'll have a look at a exercise after this. Alright, then if you have finished, let's have a look at a quick quiz. So given the diagram on the right, can you find AC and XQ? Okay, have you finished? Okay, from the angle bisector theorem applied to triangle ABC, we have AB over BD equals AC over CD, right? Because this angle equals this angle, we have AB over BD equals AC over CD, right? And in this case, we know AB, BD, CD, of course we can find AC, right? So AC should equal AB times CD over BD. And put all the values in, we have 12 times 7 over 6, which gives us 14, right? Therefore, AC equals 14. Okay, how about the next one? Okay, if you want to find XQ, we don't know the length, so it could let it be X, right? Therefore, QZ must equal 12 minus X, right? Again, if you have this angle equals this angle here, then according to the angle bisector theorem, we should have XY over XQ equals YZ over QZ. And XY is 9, XQ is X, YZ is 8, and QZ is 12 minus X. So we have a equation in terms of X. Which gives us 108 minus 8x equals minus 9x equals 8x. Therefore, 17x equals 108, and therefore x equals 108 over 17, right? Can you follow me? So this is application of the angle bisector theorem. Okay, we have already looked at the concept of incentre, inradius, and incircle. And next, let's have a look at what the area is for the incircle. So can you find the area of triangle XYZ in terms of its inradius and its side length? So suppose we have a triangle XYZ and a incircle with it XYZ. Can you find the area of triangle XYZ in terms of its inradius? Inradius is a radius of the incircle, right? Okay, so suppose the incentre is point I, and IR is perpendicular to XY, IQ is perpendicular to XZ, and IP is perpendicular to YZ. Of course, IR, IQ, IP is the inradius, right? So if we know the inradius is R, can you find the area of triangle XYZ in terms of R? Any ideas?
We don't know the side length of the triangle, do we?
Oh, the side length is 2s equals the parameter of the triangle. So if you are given the parameter of the triangle is 2s and inradius is R, can you find the area of XYZ in terms of R and S? Okay, I'll give you a hint. So those radius of the incircle perpendicular to the sides make us think of altitudes, right? So we probably could break the whole triangle into 3 parts. If you connect xi, yi, and zi, the area of xyz is given by the sum of the small areas here, right? So xyz equals area of xi, xyi plus the area of yzi plus the area of xzi, right? And for those small, 3 little small triangles, we know that's the altitude and that's the side, right? So for example, the area of xy I equals 1/2 of IR then times the corresponding side or base, which is XY, right? And the area of YZI equals 1/2 of IP times YZ, right? And the area of XZI equals 1/2 of IQ times XZ, right? Because we know IR equals IQ equals IP, all of them are length R, right? So we can put a common factor 1/2 of R in front, right? 1/2 of R times the sum of XY plus YZ plus ZX, right? And we know the length of XY plus YZ plus ZX is a parameter, which is 2s, right? So that equals 2s, and eventually that gives us r times s. Did you get it? Therefore, the area of any triangle xyz can be calculated using the product of the inradius and the semi-parameter, right? S is a semi-parameter, which is 1/2 of the total parameter. So again, this is an important property of a triangle. Let's have a look at the summaries. The area of a triangle equals this inradius times its semi-parameter, which is given by area of ABC equals RS, where R is the inradius and S is a semi-parameter. Did you get it? Okay, I'll give you 1 minute to write this down, and next we'll have a look at a quick quiz. Okay, have you finished? Alright, then let's have a look at a exercise. Can you find the radius of a circle that is tangent to all three sides of triangle ABC? Given that the sides of triangle ABC have lengths 7, 24, and 25. Basically, you're given a triangle and you know the three sides, and it asks you to find the radius of the incircle, right? Such a circle is called incircle of the triangle. Any ideas? Okay, notice that 7 squared plus 24 squared equals 25 squared, right? So this is actually a Pythagorean triple. And this triangle is actually a right triangle, right? If you have a right triangle, we could easily find the area of this triangle is given by 1/2 of its two legs, which is 7 and 24, right? And this is 84. And on the other hand, we know the area of this triangle can be given by r times s, right? Where s is 1/2 of the perimeter, which is the sum of all sides. So in this case, s is 1/2 of 36, which is 18, right? Oh, sorry. It's 56, which is 28. And put the s here, so that equals r times 28. And the area is 84, right? Therefore, we know r equals 84 over 28, which can be simplified to 3, right? You get it? You have any questions? Okay, if not, let's take a 10 minutes break, and after that, we'll have a look at the concept of medians. All right, I'll see you in 10 minutes. All right, next, let's have a look at the concept of medians. A median of a triangle is a segment from a vertex to the midpoint of the opposite side. For example, in this figure below, segment AD, BE, and CF are all medians. The medians of a triangle are concurrent at a point called the centroid of the triangle. The centroid of a triangle is usually labeled as letter G. So at current stage, we're not going to prove why the three medians can be concurrent. We're going to prove this after we learned some more concepts, okay? So as long as you know the intersection point is called centroid at current stage, you should be fine. And next, we're going to try to prove one important property of the medians. So can you prove that the medians of a triangle divide the triangle into 6 triangles with equal areas? Okay, for example, if we have a triangle ABC, and this is the midpoint of AB, then this is a median. This is the midpoint of BC. Let's call this point D, this point F, this point is E. Then these are the 3 medians of the 3 sides, right? So can you prove that the medians of a triangle can divide the triangle into 6 triangles with equal areas, which means this area equals 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 this area. Any ideas? Okay, first of all, we can easily prove that the area of BGD equals the area of CGD, right? The area of this triangle should equal the area of this triangle, right? Because this side equals this side, they have the same base, and they have the same altitude from the point G, right? And similarly, we also have the area of triangle AFG should equal the area of BFG, right? And area of triangle AEG equals the area of triangle CGE, right? Then let's assign some variables to these areas in order to facilitate our discussion. So let's call this area is X, then we know this area is also X, this area is Y, this area is also Y, and this area is Z, and then this area is also Z, right? Actually, the little triangles aren't the only triangles that share the same altitudes. Since triangle ABD, if you consider this triangle here, triangle ABD, and triangle ACD, which is this triangle here, they also have the same altitude from point A and same base because CD equals BD, right? Therefore, we also have the area of triangle ABD equals the area of triangle ACD, right? So what does this tell us? This tells us that ABD is X plus 2Z, right? ACD is X plus 2Y, right? And if we cancel X and divide both sides using the same number 2, this gives us Y equals Z, right? And similarly, we could also use the area of triangle AFC equals the area of triangle BFC, and this gives us, what is AFC? AFC is Z plus 2Y, right? BFC is Z plus 2X, and this gives us X equals Y, right? And according to these equation number 1 and 2, we could easily prove X equals Y equals Z, right? Therefore, all the 6 little triangles have the same area. You get it? Okay. In a summary, the medians of a triangle divide the triangle into 6 little triangles of equal area. So in this diagram, we have the area of AFG equals BFG equals BDG equals CDG equals CEG equals AEG. All these areas are equal. Can you follow me? Okay, this is one of the properties of the medians. And next, let's have a look at another property. Can you prove that the centroid of any triangle cuts each of the triangle's median in a 2:1 ratio, with the longer portion be the segment from the centroid to the vertex? Again, let's draw a triangle, diagram of a triangle first. So the centroid is a point of intersection of the three medians, right? So can you prove this side is actually twice of this side? Or this side is twice of this side? Can you see that immediately by using the areas we have illustrated? So if you consider this triangle here and this small triangle here, they share the same altitude from point B, right? And we know the ratio of the two areas is 2 to 1, right? So what does this tell you? This tells you the base should have a ratio 2 to 1, right? So we could say because G is the centroid and D, E, F are midpoints. So according to the previous property, we know the area of AGB should equal, because these are two small triangles, right? And that should be twice of the area of the triangle GDB, right? And the two triangles share the same altitude from point B. Therefore, we have AG over GD equals the area of AGB over the area of GDB, which means you have a number 2 here, right? So that means the length of AG is twice of the length GD. Did you get it? And similarly, this length is twice of CG is twice of GF, and GB is twice of EG. You see that? And clearly this works for any median. And in a summary, the centroid of a triangle cuts this median into a 2 to 1 ratio. For example, for the triangle shown on the right, we have AG over GD equals BG over GE equals CG over GF equals 2 to 1, where G is the centroid and D, E, F are the midpoints of each side. Did you get it? This is another important property of the medians. Okay, I'll give you 1 minute to write this down on your notebook, and next we're going to have a look at a quick quiz. Okay, have you finished? Alright, then let's have a look at a exercise. Triangle PQR is an equilateral triangle. Its side length 12. Can you find the length of the inradius of triangle PQR? Okay, I'll give you 2 minutes to think about this question, and after that, we'll have a look at the solution together, okay? So what is the concept of inradius? Inradius is a point of intersection of the angle bisectors, right? Okay, have you finished? Okay, first of all, we need to find the incentre, right? Because it's an equilateral triangle, we can let PL and RN be the angle bisectors of triangle PQR. Then because it's an equilateral triangle, we know L must be the center of QR and N must be the midpoint of PR, right? So we know this angle is 30 degrees, this angle is also 30 degrees. And the point of intersection here is actually the incentre, right? So the length of IL is a length you're looking for, which is the inradius of triangle PQR. And we know the set length is 12, and if you consider right triangle PQL, then this length should be half of the hypotenuse, right? Which equals 6. Do you get it? And if you let IL equals x, because this angle is also 30 degrees, we know QI is 2x, right? And according to this right triangle, actually this triangle is 30, 60, 90 degrees. You can use the property of that triangle to find x. Of course, if you don't memorize that, you could also use the Pythagorean theorem to help you to find that. So x squared plus 6 squared equals 4x squared, right? Therefore, 3x squared equals 36, x squared equals 12, and of course, x equals 2 square root 3, right? Therefore, the inradius of a equilateral triangle is 2 square root 3. Did you get it? Okay, then let's have a look at another property of the medians. Can you prove that the 4 small triangles in the figure on the right are congruent and that each is similar to triangle ABC? So these little strokes means D, E, F are the midpoints of the 3 sides respectively. Well, if you need that, you have to prove that. Otherwise, if you don't need that, you don't have to prove ED is actually parallel to AB. For example, if you know AF over AB equals AE over AC is 1 over 2, right? Then of course we have triangle AFAE is similar to triangle BAC by SAS similarity, right? Because angle A equals angle A. They share the same angle here. You see that? You don't have to prove any parallel lines. Or if you don't need that, you don't have to prove that. And using the similar methods, you could write similarly we have triangle FBD is similar to triangle ABC, right? The method should be the same, also SAS. And triangle CED is similar to triangle CAB. Again, this is by SAS. And of course, since each of the small triangles above have lengths that are 1/2 of the size of triangle ABC, we have FE over BC equals DE over AB, which equals DF over AC, which gives us 1 over 2, right? If you have the same ratios here, of course you can prove triangle DEF is similar to triangle ABC by SSS, right? 3 pair of the proportional sides. And since all 4 little triangles are similar to triangle ABC with the same side ratio, of course the 4 little triangles must be congruent, right?
I see how these small triangles are similar to the big triangle, but I don't understand the last step.
The last step is, since all 4 little triangles are similar to the larger one, triangle ABC, right? And the side ratio is also the same, which is 1 over 2. They have common side ratios. Therefore, the 4 little triangles must be congruent, right? So I'm not gonna write it here. And you should write this by yourself, okay? And in a summary, this is another important property of the midpoint of each side. Given that triangle DF is a medial triangle of triangle ABC as shown below, we have the following conclusions. First, triangle DF is similar to triangle ABC, and these 4 little triangles are congruent, and the ratio of these pairs of sides equals 1 over 2. And you could also prove that DF is parallel to AC, EF is parallel to BC, and D is parallel to AB. Again, we're not gonna write this here, but you could easily prove this is also true. And facts 2 and 3 are sometimes called the midline theorem. Okay, please write this down, and we're going to have a look at a quick quiz after that. Okay, if you finish, let's have a look at this exercise. So in a triangle JKL, JK equals JL equals 10 and KL equals 16. Can you find the length of the median JM and the length of the median KN? Okay, have we finished? Any thoughts in here? First of all, JM is not very difficult to find, right? Because if you have JK equals JL, then median JM is also a altitude, right? Because you can easily prove this triangle on the right is congruent to the triangle here on the left is congruent to the triangle on the right. Triangle JKM is congruent to triangle JLM, right? So JK equals JL and JM is median. This gives us JM is also perpendicular to KL, right? So if JK equals 10, KL equals 16, then KM equals 8, right? Then JM is simply square root of 10 squared minus 8 squared, which equals 6. That completes question A. For question B, well, let's call this point G here. JM and KN meets at G, right? Which is actually the centroid of triangle JKL, right? Because N is midpoint, M is also midpoint, and two medians here meet at point G. So G is a centroid, right? Remember, G is called centroid. It's not obvious how to get KN, but we do have right triangle KGM to use, which we can find KG first, right? Since G is a centroid of the triangle and JM is a median, we know GM should equal 1/3 of JM. That's one of the properties of the median, of the centroid, right? Which gives us 2. So GM is 2. And KM is 8, and then kg must equal square root of 2 square plus 8 square, which is square root of 68, which is 2 square root 17, right? And because Kn is also a median and G is a centroid, so we have Kg over Kn should equal 2 over 3. Therefore, we can find Kn equals 3 kg over 2, which is 3 square root 17, right? Did you get it? We are using this property here. The centroid of triangle cuts this median into 2:1 ratio. Remember that? So once you have found Jm is 6, then Gm is 1/3 of 6, which gives you 2, right? If you know this side, of course you can find Kg, right? And Kg is 2/3 of the whole length of Kn. Therefore, we know Kn is 3 over 2 times Kg, right? Any questions? Again, this is just the application of the properties of medians and centroid. So make sure you are familiar with all the properties we have learned today, okay? Then let's have a look at the last concept today, which is called altitude. Or sometimes also known as heights of size. And let's have a look at some properties of altitudes. Can you prove that the lines containing the altitudes of a triangle are concurrent? So actually, the altitudes of each side are also concurrent. So can you prove this is actually true? So currently we know the medians are concurrent, right? The angle bisectors are concurrent, and perpendicular bisectors are also concurrent. So if you don't have any ideas, if we could possibly show that the altitudes of our triangles are also the perpendicular bisectors or angle bisectors or medians of the size of some other triangle, then we could know that they are concurrent, right? So can you find some other triangle there? So one possible way to draw the auxiliary lines looks like this. We want our A, B, and C to the midpoints of the sides of our other triangle. Since then, the altitudes of triangle ABC would be perpendicular bisectors of the sides of other triangles, right? This means we want triangle ABC to be the medial triangle of some other triangle, since We know that the sides of a triangle are parallel to the sides of its medial triangle. We know how to make a triangle starting with this medial triangle. So we could draw lines JK, KL, and KJ and KL that is parallel to the three sides respectively, right? Through the vertices of triangle ABC, parallel to the sides of triangle ABC as shown here. And to prove that triangle ABC is indeed the medial triangle of triangle JKL, we must show that the vertices of triangle ABC are the midpoints of the sides of triangle JKL. Since AB is parallel to JK, then we have angle CAB equals angle ACK. Similarly, angle CAK equals angle BCA. Then we have triangle CAK must be congruent to triangle ACB, right? Because they share the same side. And similarly, we can prove triangle BLA must be congruent to triangle ACB as well. And triangle BLA is congruent to triangle CAK. Therefore, we have AL equals AK. So that means A is indeed the midpoint of LK. We have proved A is the midpoint of KL, right? So basically you can use the same way to prove B is the midpoint of JL, C is the midpoint of KL, using the same method. Therefore, triangle ABC is actually the medial triangle of the larger one, triangle JKL, right? Since KL is parallel to BC, altitude AD of triangle ABC is perpendicular to KL. Since AD is perpendicular to KL and passes through its midpoint, so each of AD and BE and CF is actually the perpendicular bisector of the three sides, either KL or JL and JK. Can you see that? For example, CF is perpendicular to KL, right? And C is also the midpoint of KL. So CF is the perpendicular bisector of KJ, right? And similarly, BE is perpendicular to JK. And B is midpoint, so BE is the perpendicular bisector of JL. And AD is perpendicular to KL because KL is parallel with BC. So DA is perpendicular to KL, and A is also midpoint of KL. So DA is also a perpendicular bisector of the size KL, right? So actually, the three altitudes are actually the three perpendicular bisectors of the larger triangle, right? We already know the perpendicular bisectors will cross at the same point. So BE, AD, and CF are concurrent. Did you get it? So actually we have proved like this. The altitudes of any triangle are concurrent at a point, and this point is called orthocentre. We usually denote orthocentre with letter H. So how many special centers have we learned? We have learned circumcenter, incentre, orthocentre, and the centroid, right? Be careful with the concept of each center. Okay, have you written this down? Alright, next let's have a look at a exercise that involves the concept we have learned so far. Altitudes QZ and XP of triangle XYZ intersect at point N. Given that angle YZX equals 70 degrees and angle XZY equals 45 degrees, can you find each of the following 4 angles? And if you finish, you can give me your answer in the chat box. yxp is 25, that's correct. Alright, let's have a look at the solutions together. So first one is very easy, right? From the right triangle XPZ, we have angle DXP equals 90 degrees minus angle XZP, right? So this is very easy, which is 45 degrees, right? And for question B, we can consider the right triangle XZQ. And of course, angle XZQ equals 90 degrees minus angle ZXQ, right? And this is 20 degrees, right? And question C, we could use either right triangle XYP, or we could use angle ZXP and angle YXZ. For example, angle YXP equals angle YXZ minus angle ZXP, right? And this is 70 degrees minus 45 degrees, which gives us 25 degrees. Okay, how about the last one? XP is altitude on side YZ. ZQ is also altitude of the side XY, right? The two altitudes meet at N, so we know that N is called, what's the name of that center? It's called orthocentre, right? Therefore, if you connect Yn and actually extend Yn to meet XZ at R, then YR is also a altitude on side XZ, right? Because we know the three altitude will meet at one point N. So YR must be also perpendicular to YZ, right? So from the right triangle RYZ, we have angle NYZ equals 90 degrees minus angle RZY, which equals 45 degrees, right? Any questions? Okay, because of the time constraints, for the challenging problems, I'm afraid we don't have time for that. So I'll just copy them and give them to you as part of the homework, okay? And probably next time in our next lesson, we'll spend the whole lesson talking about these homework questions, okay? Because some of them are not that easy. Sounds good? And after that, we'll move on to the next topic. All right? Okay, so don't worry if you can't complete all of them. Just try as much as possible, okay? And please try to submit your homework before the deadline, which is one day, at least one day before the next lesson. Okay, any questions, just let me know. And I'll see you next time then. Bye.